Okay, so as requested by Sarah, question 18 in the January 2019 paper. This deluge, whatever that is an event at the Winter Olympics. An athlete lies on a small sledge and races down an icy track, feet first. An athlete accelerates down a straight section of the track as shown. The track is at an angle theta to the horizontal. Draw a free body force diagram for the sledge and athlete. You should consider the relative sizes of the forces when drawing your diagram. So the first force that obviously acts on the athlete is the force of gravity, which is weight. So let's draw weight. We also know there's going to be a reaction force because every time two surfaces are in contact, they're touching, there's always a reaction force. The question is, well, how big should I draw my reaction force? I need to know that the reaction force is always at right angles to the surface, right? So it would have to be in this direction as shown. They're always at right angles. Like for example, if I have a box on the surface, the reaction force is up. That's at right angles to the surface. So yeah, so I know the direction of my reaction force, but I want to know the size because it says you should consider the relative sizes of the forces. Well, I know that he is not accelerating vertically. And by vertically, I mean like in this direction. Let's say that this direction is vertically, which is, at right angles to the slope. And let's consider parallel to the slope to be horizontally. So I know that the vertical forces have to be zero because he's not flying, right? He's not just randomly accelerating up and flying, and he's not somehow penetrating through the track. So the vertical forces have to balance. Well, to know the size of your reaction force, we need to first discuss what is the force acting downwards in this direction. And that will be the vertical component of his weight. So the weight has a component perpendicular to the track, so in this direction. And it also has a component parallel to the track. So basically, I resolved horizontally and vertically along the slope. We always say if this is theta, this has to be theta for any inclined plane. So this is going to be W sine theta because it's the angle opposite. This is a right angle triangle, and it's the angle opposite the angle, or it's the side opposite the angle. And this is going to be W cosine theta. So we said that the forces vertically have to balance. So the reaction force has to be the same size as this vertical component here. It has to be the exact same size. Okay, I know he's accelerating across or down the slope. So he's moving, he's accelerating. Yeah, meaning there has to be some sort of resultant force. There has to be a resultant force along the slope. Well, look at my forces. I have W sine theta. So actually there is a resultant force along the slope, and it's the horizontal component of the weight. So it might be tempting to just draw these two forces, but we have to, of course, consider friction because every time something is moving, there's always air resistance and friction unless the question specifies to ignore it. So there's obviously some sort of frictional force. But you need to make sure that this frictional force is smaller. So this frictional force is smaller than the horizontal component of the weight. The reason that's the case is because he's accelerating across the slope. So there is a resultant force. So that's only possible if this force is larger than that force. So let's draw all of this down below. So we said we have weight. So you got weight acting down. Make sure you use a ruler. And then we have the reaction force, and we know the reaction force has to be the same size as this component. So draw the reaction force like this. Is just a rough sketch. And then finally, friction, which is opposite towards where he's accelerating or where he's moving. And it has to be smaller than this component here. So yeah, this will be, rub this out, this is not needed. This will be your force diagram. Label the forces. So label this friction, this reaction, and label this weight. Okay, now it says the mass of the athlete is one of the factors that affects her time to complete the race. Explain why the mass of the athlete has little effect on the initial acceleration. Okay, so what is the equation for acceleration? Because we're trying to work out the effect on the acceleration. So acceleration from Newton's second law is the resultant force acting on the object over the mass. So we have to consider what is the resultant force acting on the athlete. Well, we know that vertically, i.e. along this path, the resultant force is 0. However, horizontally, there is a resultant force because he is accelerating along this direction. So let's consider the horizontal components. So you have, as we discussed before, let's say this is theta. You have F sine theta. Sorry, not F sine theta, weight sine theta. So W sine theta along the slope, and you have the friction in the opposite direction. So the resultant force is going to be W sine theta minus the frictional forces divided by the mass. So on top, I have the resultant force. Okay, now we're going to say that initially, the speed of the athlete is really small because he just about started accelerating from rest. Therefore, the frictional forces are ignored. So ignored. Frictional forces are ignored. So let's ignore the frictional force. So we're going to say this is equal to, therefore, acceleration is equal to just W sine theta, because F, we're going to ignore it because there's very little frictional forces at the beginning over the mass. Well, what is weight? I know that weight is m times g, the mass of the athlete multiplied by 9.81. So let's substitute that in. So instead of weight, m times g times sine theta over the mass. And as we could see, the masses cancel out. Therefore, the acceleration has little effect. Sorry, therefore the mass has little effect on the acceleration initially, right? Because the masses cancel out. But obviously, as the athlete speeds up, this is no longer ignored. So there will be a smaller and smaller and smaller resultant force until, of course, he reaches terminal velocity. So the acceleration would change as he speeds up. Okay, so explain in terms of forces why the athlete reaches a maximum velocity. So we're going to say the resultant force acting on the athlete is equal to the, I'll show you one last time. It's equal to the horizontal component of the weight minus the frictional forces. Obviously, the faster he's going, the larger this frictional force will be. So let's write that down. So the resultant force acting on the athlete is equal to the component of weight along the slope, which was W sine theta as written above, minus the frictional forces. We could put this as an equation. So let's say F res, resultant force, is equal to W sine theta minus F. So we're going to say that W sine theta never changes, even if he's getting faster or even if he's slowing down. That never changes because his weight is constant. So W is always constant. And theta, the angle along the slope, never changes. It's always constant as well. So we're going to say that W sine X never changes with his speed. However, as he speeds up, the frictional forces increase due to air resistance increasing. So the resultant force acting on the athlete will decrease until W sine theta is equal to F, right? Is equal to F. There is no longer a resultant force, or the resultant force is now 0. So the acceleration is 0. this is when he has reached his maximum velocity. Could add more detail. I think I already added too much detail, just because I want to make sure I score all 3 marks. It is stated that the maximum speed is greater for athletes of greater mass. Suggests why this is only correct up to a certain mass. What I'm going to say is, after a certain point, it is impossible to increase the mass without increasing the volume. Right, let's say you have the maximum density of a human. You cannot have a larger mass without having a larger volume. And we know a larger volume will mean he's going to or she's going to experience more air resistance. A larger volume will mean the athlete will experience larger frictional forces. And I guess this answers this question. So larger frictional forces, that's going to stop him from reaching a higher maximum speed for a higher mass. Actually, there's one more question. This question 10. Okay, a student used a balance to measure the mass of a small cube with sides of length x. The student also measured the mass of a larger cube with sides of length 1.5x. Which of the following is the density PL of the larger cube in terms of the density PS of the smaller cube? So he wants the density of the larger cube in terms of the density of the smaller cube, meaning I need the expression for the density of the larger cube and expression for the smaller cube and see how are these two expressions related. So let's start with the smaller cube. So density of the smaller cube is equal to, obviously, the mass of the smaller cube divided by the volume of the smaller cube. The mass of the smaller cube is just 0.05 kilograms. And the volume, well, it's a cube, right? A cube has the same length and width and height. So it's just going to be x times x times x, which will give you x cubed. So this is the volume of the smaller cube. Whereas for the larger cube, so let's do the larger cube. The density of the larger cube is the mass of the larger cube over the volume of the larger cube. Well, the mass is still 50 grams, which is 0.05. And the volume is the length times length times length, which is 1.5 cubed. So 1.5x cubed. Let's simplify this expression, and let's say that this is equal to 0.05. Let's cube the 1.5 and also cube the x. This will give me 1.5 cubed x cubed. And I'm going to write this in a slightly different format. So I'm going to write this as, this is the same as 1 over 1.5 cubed multiplied by 0.05 over x cubed. All I did was I took the divide by 1.5 cubed outside. Good. But we know that PS, the density of the small one, is equal to 0.05 over x cubed. So notice how this is seen over here. So we could write this as PL is equal to 1 over 1.5 cubed multiplied by the density of the small one, PS. Why? Because PS, this is what PS is equal to. And then you put this in your calculator. So put PL is equal to 1 over 1.5 cubed multiplied by PS. So let's put that in my calculator. 1 over 1.5 cubed is the same as 0.296 density of the small one. So that is what the density of the large one is equal to, which obviously rounds to 0.3. So the answer is D. I hope this helps.